this video, we're going to see how we can create new features based on existing features and transform the values within the features we have. So let's take a look at the reading. And of course, skewness is one of the big issues we're dealing with, especially when working with any kind of modeling algorithm that relies on the linear assumption of normality. So skewness is an issue, and if we have positive skew or negative skew, we can either use square root, cubed root, or a log, natural log, or square it, cube it, or raise e to the power of the value to help correct those skews. All right, let's take a look and see what we can do in RapidMiner. But before we get there, let's review the descriptives for our lending club data. Okay, so here we can see, and I highlighted these in yellow just to bring them to my attention. For the revolving balance that we're using as maybe a predictor to the loan worthiness of a potential loan applicant, we can see we've got a kurtosis of 183. That's excess kurtosis, so the actual kurtosis is 186, and skewness of 9.68. So that's pretty good skewness. Here we can see accounts now delinquent with skewness of 24. Wow. All right, maybe I should have chosen that one. But so we've got a good range of skewness in our data, total collected amount, skewness of 16. So let's take a look at that revolving balance. And that's based on this column here, column T. All right, so I took the liberty of moving that column over here, and then I ran some calculations to calculate the square root of each value, the cube root, and then the natural log. So after I made these conversions to the revolving balance, I reran the descriptives, and you can see in each case, both the kurtosis, well, not in each case, the kurtosis ended up going back up, but the skewness came down in every case, and it came down for square root and cube root for kurtosis as well, and then went back up with the ln plus 1. So the reason ln plus 1 is a good one is in some cases you may find a value of 0, and ln of 0 is uncalculable. So what I have had this formula do is I take the value of ln, the number itself, plus 1, and that allows me to resolve that potential problem. Another thing, you can see the revolving balance. It's pretty obvious. It's a pretty highly skewed data set or feature right here. But even with square root, you can see it starting to become more normal. Cube root definitely is the best fix. And then ln plus 1 actually moves it too far the other way. So we end up with a little bit of negative skewness. Okay. So with that in mind, we would want to cube our revolving balance. So let's do that in RapidMiner. And in RapidMiner, we could go back. Let me see. I think I've got it open somewhere. Yeah, there it is. I can actually look at this and look at my revolving balance as well. And see, this is a pretty highly skewed data set. I've got 10 bins, but if I change this to 25 bins. Yeah, now you can see, let's make it 50 bins. And yeah, you can see how skewed this data is. All right. So let's create a new feature, and this will be the cube root. of revolving balance. So I'm going to go down here to, I think, blending, attributes, generation. So I'm going to generate a new attribute. And I will keep all the columns I have. And this is a good time to make a point. Anytime you generate a new attribute, you want to keep the original attribute. Also, if you do any kind of data cleansing like removing outliers, you should do that in a new feature and keep the original feature that included the outliers, because at some point, if you have more data going forward, those outliers may not be outliers anymore, or your outlier threshold may change. So it's important to try and keep a good trail of breadcrumbs that allows you to go back to any step along the way and pick up with that data. All right, so in this case, I am going to create a new column name. I'll call this revolving balance. I think that's what it is, REVOL_BAL cubed, for lack of a more creative name. And then I'll bring up this expression builder, and I can use this to build my expression. I can do just a regular math function. So I've got square root. I've got a power that I can raise. I don't know if I have cube root or not. Okay, so no, I don't. So I'll raise the number to a power. And I'll do that by just clicking on power. And then the number I want is that revolving balance. If I forgot what the name of the attribute is, I can just go and find it here and click on it to bring it into my function that I'm building. So these functions work a lot like you would in Excel or any kind of a scripting or programming language. They require the attributes or the parameters to make the function work. So I've got the revolving balance as the value. I'll put a comma in for my second value, and I want to raise it to the 1/3 power, which is basically a way of saying I want the cube root. Okay, so now I can apply that. And also you can see it tells me the expression is syntactically correct. So that's an important distinction. Yeah, the expression is going to work and do something. Now, is it going to do exactly what you want? Well, maybe not. So you may have to play with it. But I think we're going to get what we want here. So I apply it. And now I can run my process, look at my fields, and I did this with revolving, what did I do it with? Revolving balance. So I've got revolving balance down here, still nice and skewed. And I've got a new feature that I just generated called revolving balance cubed, which looks much better. And this is, what did I do? 75 here, maybe. So a bunch of different bins. So this is more reminiscent of that chart we saw in Excel right here for the cube root. All right, so that is generating a new attribute. Another thing that may pop up that we want to be able to address is the ability to use a consistent scale, especially when it comes to distance calculations for clustering and k-nearest neighbors and things like that. The scale of each feature can play an outsized role just depending on how big the range is. So in this case, let's take a look back at what we have here, and we've got ranges, 6 for lone status numeric. Actually, I would not really want to consider a numeric version of a categorical for distance calculations. We can do it, just because, numbers, we can assign numbers arbitrarily or maybe in some ascending order, but I generally try to steer clear of it if I can. If you want to use categoricals, it's much better to just create dummies for each value of the categorical and go that way. Okay, so loan amount, we've got a range of 39,000, 1 to 40,000. Interest rate, got a range of 25.68. So you can imagine if I'm just using these two, the difference in loan amount is almost always going to dominate the distance calculation. So let's standardize a fair number of these ranges to a standard range. And we often call this normalizing the data, although I hate that term just because there's so many other things we do that we use the term normalizing for. We can normalize a database design with the third normal form and normalization. We've got that normal distribution we've already talked about for data. So I like standardizing or rescaling the data. But even so, if I decide I want to standardize these ranges, the tool I'm going to use in RapidMiner and a lot of other these types of tools is called Normalize, of course. All right, so I will normalize all of my data ranges, and then, I'll select a subset of attributes that I want to do. So let's just pick some of the most important numeric ones. So let's say loan amount. Interest rate, we just looked at. Some of the other ones, what's the installment? Total payment, total received principal, total received interest, total received late fees. The applicant's annual income. How many accounts are now delinquent? How many open accounts do we have? Do they have? What's their revolving balance? What's their revolving utilization? So this is a fair number of different numeric values with wildly different ranges. So let's apply that. And then we've got a number of transformations. I can use an IQR approach, which basically uses the interquartile range. I can do a Z transform, which is a pretty common one, very popular now. 10H is another one, but that is not in this particular one. I can transform it to any kind of a range that I specify with any minimum and maximum value. So this is a min-max approach. If you leave it at the defaults, 0, 1. I could do a proportion transformation. So in what proportion does everyone show up in its particular distribution? But a Z transform is a pretty good one. And you can see here the Z transform sets the mean to 0 with a standard deviation of 1. So you're not going to be bound between -1 and 1, but the bulk of your data should reside within that range. You've got the other ones here that are described in a little bit more detail. So let's go ahead and run those through. And now we can see my interest rate, my loan amount all show up as basically where they stand on the distribution. Is it lower than the mean, higher than the mean, and by how many standard deviations? So that is a good one to use. A lot of people use it. If I were to do a min-max at 0 and 1, that's another real commonly used one. And now everything's going to show up as some value between 0 and 1. Okay? So that is standardizing the range of values for a feature, but called normalizing in RapidMiner and the lingo of lots of other tools as well. All right, so that's it for this video. Let's get back and see what we'd like to do next.